there's one more really important thing. I have to talk about the divergence of this equation before I do a few examples. So, for a positive charge, we already know that the divergence of it around its center area is positive. It returns a positive number. But let's say I ask for the divergence right here. What would this be? Well, what happens is it turns out to be 0. Now, it's going to sound a little weird, but intuitively, it's a little hard to visualize this. So if this was, pretend, your arrow coming out in 3 dimensions, if I were to draw a volume over this area in space, you're probably thinking, wait a minute, by E is equal to KQR squared, R hat. The amount of flow in is actually greater than the amount of flow out. So the divergence of E at this point in space is less than 0? And actually not. What happens is, for this equation right here, the differential form of the electric field, it only gives you rho right around the center, which is basically your charge density. Anywhere else, any other region of space outside of this center area is actually equal to 0. Now, with the vector field example, I don't have a clear explanation on why this turns out to be 0. But when I modeled it mathematically, it did work out. What happens is I modeled the electric field vector as E of xyz, and then I did kq over r squared. But remember, the electric field is in 3 dimensions. So when we do r squared, I did x squared plus y squared plus z squared square root to find the distance r emanating from that source. And then this is the area we're finding right now. But we still have to multiply by r hat. So when we multiply by r hat, you have to do x over this entire square root, y over this entire square root, and z over this entire square root. Now, when I did this, and I did the gradient of this, so by taking the gradient, what I'm actually doing is I'm taking the derivative of this in the x component plus the y component plus the z component. When I'm actually taking the derivative of all these terms, it mathematically worked out to be 0. So I'm going to fall on that thinking, even though my intuition isn't fully clicking into place here. I can explain this using field lines though. Imagine if instead I did the positive charge not as vectors, but as field lines emanating from a source. Now, when I enclose this volume of space right here, notice the amount of field lines entering the surface is always equal to the amount of field lines exiting the surface. That's another intuitive explanation you can use. So, let's get back to Gauss's law. How does this work intuitively with the divergence theorem? With the divergence theorem, let's start off with the most basic example. So let's say you have a plus charge right here. And here is your Gaussian surface. So let's just choose a sphere, a perfect sphere. And here are your electric field vectors flowing from this source. And here is where the vectors, electric field vectors, contact the surface. So imagine, this is your volume, this is your area element, dA. So then, in this situation, your vector is n hat. And we're summing up all these elements, dAs, by first dotting the electric field vector with the n hat vector first. So here's another dA. And here's your n hat.
Presenting the what?
And now, notice that when you compute the flux over the surface, you're doing E dot n hat dA. That turns out to be a positive number because when you sum up all these little dot products, for all these areas, E is always parallel to dA. And so then the cosine between them turns out to be 0. So we knew that this is equal to a positive number. But what about if we use the divergence theorem? Will it give us the same answer? It will give us the same positive number, and here's why. By the divergence theorem, we can write it in terms of this form. So we're going to sum up the divergences, or the sources, over this volume. And now, instead of dA, I'm going to enclose the charge right here with a volume dV. So this volume, let's call this d volume 1. And here I'm going to create another volume right here. That's called d volume 2. And then you notice, when we're summing up the divergences over the volume, there is the divergence for d volume 1. So in this case, you get a plus rho. You get a plus rho for this d volume right here, for d volume 1. But notice, for the other d volumes, it's 0. Even though the electric field, let's say, flows into this area, as we have shown just before, this d volume is 0. And the same thing goes for all the other d volumes in this space. There's no charge enclosed there. There's no sources or sinks. That's why when you sum them up all using the triple integral, they all turn out to be 0, except for the plus charge located in the center. And in this plus charge, because there's only one, it turns out to be your plus Q. It turns out to be the plus Q over the center, over E naught. And it gives you the same answer as in Gauss's law. And now, because this is a plus Q, this is also equal to a positive number. But let's say I create a different situation where you had both a positive charge enclosed in the sphere, and as well as a negative charge. So in this case, here's your surface again. Actually, I have it right here. So here's a plus charge and a minus charge located just slightly offset in the sphere. And now, the electric field vector gets shorter as you move away from the charge. And notice, this is actually an electric dipole. So the electric field vectors bend around, flowing out of the positive charge before circulating back in and flowing into the negative charge. And notice, the dA is slightly offset, but do you notice that in this case, your normal vector is out like this. Your normal vector is out. And so there's a slight angle in between them. Same goes for this one. And here I'm going to call this angle theta 2. But notice, for symmetry reasons, I just kind of shifted them offset so that the angle between this for the positive charge and this for the minus charge, they're the same value. And the same thing goes for theta 2. Now, if you were to sum up the flux on this surface, I'm not going to mathematically do it, but when you sum them up, you would do the electric field of this red right here. Let's call this E1. And at this point, let's call this E2. And the same thing goes for the blue. Same thing goes for the blue. So let's call this E2. E1 right here. And let's call this E2. So when you take the dot products of all these little dAs, what you're actually doing is you're doing E1, the magnitude of E1, times n hat. And where the magnitude of n hat is just 1. But now you're finding out the angle in between them. So you have cosine of theta 1. And then you do a plus, and you also do it for the other positive electric field vector, n hat, and then cosine theta 2. And the same thing goes for the negative electric field vector. So this is E2, same thing as before, E1, sorry. N hat, cosine theta 1. But notice, in this case, E1 and n hat, they're in the same direction, sort of. They're separated by an angle theta, but the dot product is positive. But in this case, notice how, although the angle between them theta 1 is the same, Notice how n hat and E1 are pointed in a different direction. So the angle between them technically is greater than 90 degrees. That means this dot product is equal in magnitude but opposite in sign to this dot product. And the same thing goes for this dot product too. This is the minus of this. Let me add the dA's in here because you're multiplying by dA. So that means these two values actually cancel out to 0. And these two values also cancel out to 0, which means the net flux through that surface is 0. Note that the electric field isn't 0. The electric field still exists. It still flows from the positive source into the negative source. But the flux turns out to be 0. And if you want to think about it in terms of the divergence theorem, it will also give you 0. Notice, let's say I enclose a volume again around this source, positive source. Let's call this D volume 1. Let's call this D volume 2, which surrounds the negative source. And again, I can have other D volumes. Let's call this D volume 3. Now the divergence, because this is a triple integral, we're summing up all these little D volumes. But we're taking the divergence of the electric field from within that D volume. So in this case, this would be a plus rho emanating from that positive charge. But then, notice, when I do it for D volume 2, it becomes a minus rho over epsilon naught. And then, just as we've shown before, for all the other D volumes, because there's no charge enclosed, although there's an electric field there, the divergence of that is 0. So you just have a bunch of zeros after zeros over here. Notice, these two cancel out too, because you have the same number of charges in these volumes, and you have the same density. That means this also ends up going to 0. And so your divergence, when you compute Gauss's law using the divergence theorem, it gives you the same answer as if you brute force calculated it using the flux integral. Now, what would happen if, let's say, I decided to do this example, but I added another positive source in? I'm going to do that later.